Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the nascent intellectual firmament of computing, where the architecture of machines commanded the primary focus, the 1951 publication of the preparation of programs for an electronic digital computer by Maurice, Vincent, Wilkes, David Wheeler, and Stanley Gill constituted a foundational moment. This work, emanating from the University of Cambridge Mathematical Laboratory and its pioneering EDISAC computer, was the first textbook to systematically articulate the principles of software creation. It proposed that the act of programming was an intellectual discipline with its own methods, structures, and philosophical underpinnings. This essay provides a direct evaluation of the book's internal claims and conceptual frameworks, proceeding section by section to analyze the arguments that collectively transformed programming from a bespoke, arcane craft into a structured engineering practice. The analysis will assess the coherence, foresight, and methodological rigor of the claims presented by Wilkes, Wheeler, and Gill, examining how they constructed a complete and durable paradigm for software development. Section 1. The conceptualization of the stored program, computer and its orders. The book commences with a lucid exposition of the EDISAC fundamental architecture and its order code. The central claim advanced in these opening chapters is that a finite, comprehensible set of elementary operations provides the complete toolkit for expressing any computable problem. The author's evaluation of this claim rests upon their pedagogical method. Their presentation is concrete and grounded in the physical realities of the machine, describing the main store as a set of 32 mercury delay lines, each holding 32 numbers of 35 binary digits. This tangible description demystifies the machine, presenting it as a logical, deterministic system. The argument for the sufficiency of the order code is made through demonstration. Wilkes, Wheeler, and Gill detail each instruction, from addition and subtraction to logical shifts and conditional transfers of control. Their approach involves explaining the functional purpose of each command within a computational ecosystem, showing how simple instructions for moving a number from the store to the accumulator, when combined with conditional orders, create the possibility for complex, non-linear execution paths. The evaluation of their logic is overwhelmingly positive. They successfully translate the abstract theory of universal computation into an accessible, practical framework. They argue that mastery of these 17 basic orders empowers the programmer with complete control over the machine's behavior. The evidence for this claim is the implicit promise of the chapters that follow, where these atomic instructions are composed into powerful, sophisticated programs. Their treatment of binary arithmetic and memory addressing is meticulous, establishing a baseline of technical literacy required for the more profound concepts to come. The authors effectively claim that a programmer, armed with this foundational knowledge, can reason about the state of the machine at any point in a program's execution, a prerequisite for the disciplined approach to debugging they will later champion. Section 2. The formalization of the subroutine and the library. This portion of the work contains its most revolutionary and enduring contribution, the formalization of the subroutine as the primary instrument for managing complexity. The core claim is that the decomposition of large problems into smaller, self-contained, and reusable routines is the most effective method for developing complex software. The authors propose a complete system for this modularity, a system whose brilliance lies in its detailed mechanics. The primary evidence for their claim is the invention and thorough explanation of the Wheeler jump, a sophisticated linkage convention. This convention, a sequence of orders placed at the start of a subroutine, ingeniously uses the program's own code to store the return address. A specific instruction plants the address of the instruction following the subroutine call into a designated location within the subroutine itself, which is then used for the final jump back to the main routine. This mechanism establishes a formal contract between the calling code and the subroutine, enabling true encapsulation. The evaluation of this claim reveals its profound insight. It is the first articulation of what would become the application programming interface, or API. The authors argue that this technique permits programmers to work independently on different parts of a larger program, trusting the defined linkage convention to ensure correct integration. This directly addresses the problem of scale in software development. Further strengthening this argument is the concept of the subroutine library. Wilkes, Wheeler, and Gill claim that a curated collection of pre-written, tested, and documented subroutines for common tasks like decimal to binary conversion, printing, and calculating trigonometric functions drastically accelerates program development. The library itself, meticulously catalogued in the book's appendices, serves as an irrefutable demonstration of the concept's power. A quietly revolutionary act, such as printing a neatly formatted table of prime numbers, is shown to be achievable by assembling a few calls to library routines, an immense leap in programmer productivity. Their argument is further solidified by the design of the initial orders, a precursor to the modern operating system's bootstrap loader. This short, hardwired program, permanently stored on uniselectors, was responsible for loading the rest of the program, including the subroutines, from punched paper tape. Its most crucial function was to perform the relative addressing, dynamically adjusting memory references within subroutines so they could be loaded into any available part of memory and still function correctly. This claim of position independence for subroutines is a cornerstone of reusable software, and the authors provide a complete, working mechanism to achieve it. The evaluation of this section concludes that the authors successfully constructed and defended a comprehensive system for modular programming that remains, in principle, the foundation of all modern software engineering. Section 3. The pragmatics of program development and debugging. Having established the architectural principles of good program design, the authors turn their attention to the human process of its creation and correction. The central claim of this section is that program correctness is an engineered quality, achieved through systematic checking, the use of diagnostic tools, and a disciplined, logical approach to the identification of errors. The book moves the conception of programming beyond the mere transcription of an algorithm into code. It acknowledges the fallibility inherent in the human act of programming. The primary evidence for this claim is the author's advocacy for specific, practical techniques. They introduce the concept of the post-mortem routine, a diagnostic tool that, upon a program's halt due to an error, prints the contents of the accumulator and key memory locations. This is the direct ancestor of the core dump. The value of this technique, they argue, is that it provides a static snapshot of the machine state at the moment of failure, transforming the debugging process from guesswork into a form of forensic analysis. The evaluation of this argument highlights its foresight. The authors are the first to treat debugging as a science. They outline methodical approaches, such as inserting extra print orders at intermediate points in a program to trace the flow of execution and the values of variables. This technique, which they call proving, is a foundational method of verification. They also discuss the importance of checking input data for validity, an earlier articulation of defensive programming. There is a subtle, almost dryly humorous acknowledgement of the programmer's psychology, noting the tendency to assume the machine is at fault. The authors gently, but firmly, counter this by claiming that nearly all errors are errors of logic made by the programmer. Their proposed methodologies are designed to help the programmer find the flaw in their own reasoning. The logical coherence of their argument is impeccable. By providing a structured method for both building programs via subroutines and for diagnosing their failures via postmortems and proving, they present a complete life cycle for software development. The evaluation confirms that Wilkes, Wheeler, and Gill were successfully codifying the unwritten folklore of the Cambridge laboratory, transforming the dark art of finding bugs into a communicable and teachable engineering discipline. Their claim that a disciplined process yields reliable software is validated by the sheer existence of the extensive and functional Evisec subroutine library they themselves had built using these very methods. Section 4. The scope of applicability and early scientific computation. The final major section of the book aims to prove the utility of the entire system by demonstrating its application to significant scientific problems. The core claim here is that the EDISEC, programmed using the subroutine-based methodology, is a powerful and versatile tool for advanced research, capable of solving problems previously intractable due to their computational burden. The evidence presented takes the form of fully worked examples, most notably the numerical integration of ordinary differential equations, by walking the reader through the construction of a program to solve, for instance, the equation di by dx equals the function of x and y. The authors showcase the practical payoff of their entire philosophy. They demonstrate how a complex mathematical task is broken down. A main program implements a numerical method like the Runge-Kutta method, but it does so by calling library subroutines. A routine is called to evaluate the function of x and y, another to handle the printing of the results in a readable tabular format, and others for any necessary elementary functions. The evaluation of this section's claim is that if functions as a powerful, culminating proof of concept, the examples are chosen with care to be non-trivial. They are legitimate scientific computations that would have taken a human computer weeks or months to perform. The author's argument is that the abstraction provided by the subroutine library allows the programmer to focus on the high-level logic of the mathematical method, freed from the low-level details of input, output, and basic arithmetic. The logical coherence is compelling. The success of these application programs directly validates the claims made in the preceding sections about modularity and reuse. They also include examples from other domains, such as the generation of tables of mathematical functions, which further broadens the demonstrated scope of applicability. The book thus claims that the stored program computer is not merely a high-speed calculator, but a general-purpose symbol processing device, a claim substantiated by programs that do more than just crunch numbers. They format output, manage data flow, and assemble themselves from modular parts. The evaluation confirms that this section successfully bridges the gap between the theory of programming and its practice, providing convincing evidence that the intellectual framework developed at Cambridge was ready to fuel the scientific and engineering advances of the coming decade. In conclusion, a meticulous evaluation of the internal claims presented in the preparation of programs for an electronic digital computer reveals a work of extraordinary coherence and profound foresight. Wilkes, Wheeler, and Gill constructed a complete intellectual paradigm for the creation of software where none had existed before. Their initial claims regarding the sufficiency of a basic order code establish the computer as a deterministic and knowable system. Building upon this, the central and most powerful claim, the formalization of the subroutine and its library, provided the crucial abstraction necessary to manage complexity and enable collaborative, scalable software development, a claim substantiated by the elegant mechanics of the Wheeler jump and the position-independent loading enabled by the initial orders. They further claimed that program development was an engineering life cycle, requiring disciplined methods for debugging and verification, an argument they convincingly supported with the introduction of systematic techniques like the postmortem. Finally, they demonstrated that this entire methodological apparatus was of immense practical value, capable of solving significant scientific problems, thereby validating their entire system. The enduring significance of the work lies in its success at defining the very ontology of programming practice. It established the vocabulary, the core techniques of modularity and reuse, and the foundational philosophy of software as an engineered artifact. The book's clear, logical, and internally consistent arguments did more than document the practices of the EDISEC group. They provided the definitive intellectual blueprint that would guide the evolution of programming into the discipline of software engineering.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.